So I have just made a couple of notes for the paper Digital Accelerating the Pathway. I'm going to go through what I found was interesting. So basically, we are talking about STEP, which is the spherical tokamak for energy production. It kind of looks like this in the end, and we want to talk about how we can use digital tools to kind of accelerate the process and make it a bit more to see how digital tools can actually help us build it, because it's very hard to build it. Like, it's the first device we've ever made, like a fusion reactor. So you can't exactly build it and then test things out. Well, you can, but it's better to test things out before you build it so you can hopefully build it better. So in the paper, I just highlighted some yellow points which I found interesting. And one of the key concepts in there is a digital twin and a digital shadow. So in a way, a digital shadow, in my opinion, is like one part of a kind of process, like part of a span analogy. It's like a digital representation of something, usually very one-dimensional. And a digital twin tends to be a bit more complex, where it can do a lot more stuff. Like, think of a digital shadow as, imagine we have like a logistics company who is tracking their van. They just need a signal every so often at deliveries to, okay, you've been here, you've been here, you've been here. It doesn't really need to be more than that. Whereas a digital twin oftentimes needs to be almost like a full working version of the physical phenomena you're trying to model. Like, imagine a heart, for example. And just keep in mind, really try and think of it like just a fancy model or a fancy simulation. And I say fancy as if it's nothing, but it gets really complex, but just think really good model, basically. So I took an example from a paper I read a long time ago about, I think it's heart, and then in it they mentioned creating a digital twin using an exascale computer, which we'll come to a bit later. Like, a blood vessel can be modeled with some maths, some very complex maths, but not too much. But to get it operating in the whole human body is much more challenging. Because at some points there's faster blood flow, there's bigger veins, there's bigger this. All this stuff is things that need to be considered. And you can see in the digital twin diagram, to go from this to that is a lot of maths. And I think the more maths you have, the better you can represent. The more maths, the more code you have, the more RAM you have, the better you can represent a physical phenomena in code. And the better you can model the physical phenomena in code, the better the results you can draw from this, basically. So that is kind of how I'd explain digital twin. Now, in the case of plasma, I'm not the best at plasma yet, but I think try to imagine it similar to the blood analogy. We're going from a very, very simple thing, we're going to a very, very complex thing that needs to be modeled. We have a couple of open source systems that we have already designed. Somebody smarter than me has spent more time trying to design it, so there's probably a lot of code behind it. And even this thing, the Helm BC, has got like a GitHub with lots of code in it, so there it is. These models basically are a series of functions all put together. So imagine, if I can get it drawn out. Imagine not just one model, but like hundreds of models put together. So model 1, model 2, model 3. This gives you inputs, this gives you inputs, this gives you inputs, this gives you inputs. That's kind of like how you should imagine it, but really, really big. And each model, although it's simple, is like so much inside of it. And then you can see here a couple of key areas to focus on. It's more the physics side of things, and I chose a biology example because I understood it best and I felt it was easiest to explain it. And then the digital twin, you can see my very simple diagram is much more explained in detail here. So it's like, okay, how do I handle all these parts now? How do I do the pressure? How do I do the temperature? How do I model it exactly? How does the software work? How does the sensor work? All this complexity needs to kind of be put together. And once we have an accurate model, or I suppose our model starts out very inaccurate, but after a while it probably gets more accurate. And there's probably a point where it becomes usable in the real world, basically. Like this heart, for example. I'm sure at some point now we can start using this to draw some conclusions or make some tests. It may not be perfect, but it's better than what we had yesterday. And I think it's on the path to mapping out a full heart. So Here are some more tools to explain. Again, it's plasma simulation, material simulation. It really is just the same process. Take a physical phenomena in the world, try and map it to code. And then, yep, same thing. And the advanced simulations, again, I'll explain how it gets. Okay, high fidelity simulations also provides the capability for in silico validation. So, in the analogy I gave you earlier about the truck going to different places, that's so simple. It's like basically a thread and process. Send message, receive message, that's it. Basically it. Now, the heart is way more complex. Like there's maths here, maths here, maths here, and it all has to interact with each other properly. So, when it comes to computers now, let's take a GPU. Let's assume a GPU has some memory, and has a brain, and has instructions. So you might be thinking, well, one GPU is enough. No, we're talking like thousands of GPUs need to be connected, need to talk to each other to be able to simulate a world. Like my Sudoku solver problem that I did a long time ago, it kind of tries one option, tries another option, tries another option. It basically brute forces this, and that's really, really simple. But for high particle physics, high fidelity, the more data I can accurately model, like in the heart, the better the result comes. But to model this data is very, very difficult. It takes time to learn how to best represent it. It takes a lot of computing and RAM to actually model it, and energy to run the things. So digital twins, in my opinion, are pretty good. But to do like the harder task, which require a lot more data and math, such as particle physics, because I know CERN has like so many thousands of petabytes of data a day, that is very hard to manage. Yep, and to note now, a lot of simulations require exascale computing facilities, like the human heart now. To model this properly takes a lot of data, like a lot of data, a lot of GPUs. But for the most part, simulation is pretty much numerical. We can boil it down to a set of functions, which will just be function x, input, output, and it's got a range. So there's a range of possible versions the heart can be in. You run it in function fx, and it gives you an output. That's basically it. But fx can be made of like millions of different fx's. And that's kind of what I got from Digital Twin.